the reaction quotient. Good grief. Reaction quotient. I've typed the word reactant too many times. How can we predict the direction of change if we have a reaction mixture that's not at equilibrium? And you've got both reactants and products. If you only have reactants, you can predict it's going to form some products. And if you only have products, you can say, well, yeah, it's going to go in the reverse at least a little bit. But what if you have all of them? What's going to happen? Well, the reaction quotient helps us to figure that out. And it is calculated exactly the same way that you calculate an equilibrium constant. The difference is the reaction is not at equilibrium. So we're calculating an equilibrium constant, but it's not at equilibrium. And so we can't really call it an equilibrium constant. It's not constant, and it's not at equilibrium. So we gave that a different name, reaction quotient. QC or QP, and so it can be in terms of concentration or in terms of pressure. So QC is going to equal the concentration of the products raised to the powers of their coefficients divided by the reactants. At equilibrium, that reaction quotient will equal the equilibrium constant because all the concentrations will be the equilibrium concentrations. So let's look at this graph. Graphs are awesome, but sometimes you just need to look at them a while and figure out what on earth is this, right? So let's examine this. Here, we're looking at this reaction. A is in equilibrium with B, and so we've got blue and we have red. The reaction quotient is going to be the concentration of B divided by the concentration of A. That's the same form that we would have for the equilibrium constant. The difference is that these concentrations don't have to be the equilibrium concentrations. And then the graph itself. Here we have Q or K going from 0 up to 3.5, and over here we have concentrations. And we're looking at the concentration of A and the concentration of B. If we start with A at 1 molar, then as time goes on and the reaction proceeds, the concentration of that reactant is going to go down. If we start with a product concentration of 0, as the reactant proceeds, the concentration is going to go up until all of the reactant has been converted to product, right? So this red line here represents the equilibrium constant. K equals 1.45. This is a line with a slope of 0 because it's a constant, right? We saw that no matter what you start with, if you wait until it's at equilibrium, that expression gives you the equilibrium constant. So this is not changing at all. Let's look at what happens down here. If we're starting with 1 mole per liter of A and 0 of B, then what is Q? Q equals the concentration of B over the concentration of A, right? So that's going to be 0 divided by 1, which is 0. So here we see that Q is 0. All we have is reactant. As the reaction proceeds, or as we increase the concentration of decrease A and increase B, then this quotient gets larger, right? Because B is going up, A is going down. So this Q gets larger and larger. At equilibrium, it crosses where the equilibrium constant is. And then it keeps going. Where's it going to end up? At infinity. Because over here at the very end of the graph, Q is going to equal 1.00 divided by 0.00. That's undefined, but that's infinity, right? As it goes on, it gets closer and closer to infinity. where does the reaction want to be? At equilibrium. So if we look at a particular combination, maybe equal amounts of reactant and product, we can calculate Q. Q will equal 1 for that situation. That is less than the equilibrium constant, which tells us Q will continue to increase until it gets to the value of the equilibrium constant. So in this situation, the reaction will go to the right towards the products until Q equals K. If we have a situation over here, say where we have 3 times as much B as we have A, so we have a reaction quotient of 3. That is larger than the equilibrium constant. The reaction will proceed to the left towards the reactants until the reaction coefficient has decreased to equal K. So the reaction coefficient tells us, is this reaction going to go forward or is it going to go reverse? How is it going to get to equilibrium? Any questions? The reaction quotient relative to the equilibrium constant is a measure of the progress of a reaction toward equilibrium. If Q is smaller than K, the reaction goes to the right towards the products because it needs to get bigger. If Q is larger than K, the reaction will go to the left towards the reactants, making Q smaller and smaller until it hits K. And if Q is equal to K, then the reaction is already at equilibrium and nothing's going to happen. So consider this reaction and the equilibrium constant. Here we have a reaction mixture that's got some reactant and some product, and we're asked to calculate QC and determine the direction in which the reaction will proceed. So the formula for QC is the same as it would be for KC. The concentration of the product, NO2, this has a coefficient of 2, so this needs to be squared, divided by the concentration of the reactant, N2O4. That has a coefficient of 1, so it has an exponent of 1. So this is the mixture that was originally put together. So we've got 0.0255, that's squared, divided by the concentration of the other one. Oops. I'm coming up with 0.0196. Anybody else? Okay. What do we do with that number? We compare it to KC. Maybe it would be helpful to write this in scientific notation. So, is this one bigger or smaller than KC? It's bigger. So we've got QC is larger than KC. So you can memorize that summary on the previous slide, or you can think about it. So these concentrations are going to change until they get to this, until this expression is equal to this. This number is smaller than this number. So if this needs to go down, then the product number needs to get smaller, right? And the reactant number needs to get bigger. Then QC gets smaller. So that tells me the reaction is going to go to the left, towards the products. Any questions? Yes?
I think I have my left and right confused. Wait. Towards the left, towards towards the reactant?
No, I have my mouth confused. Thank you. Sorry, towards the reactants. Yes? It's confusing enough without me doing that to you. Did I mess up anything else? No? Okay. Well, that's pretty good. Only one screw up per slide. Yeah.
So when you say it goes to the left, you mean on that graph?
What I mean is the reaction as written here, it'll shift to the left. It'll proceed in the reverse direction. So this reaction being in equilibrium can go to the right or to the left. It'll go to the left. Yeah. Yep. Any other questions?